Now we're going to talk about rate of change applications. So our learning outcomes are apply rate of change to displacement, velocity, and acceleration of an object moving along a straight line. Predict the future population from the present value and the population growth rate. And use derivatives to calculate marginal cost and revenue in business situations. So moving along the line, we talked about before position functions defined by S of t, and that the velocity is going to be the first derivative of the position function S prime of t then. Now speed is different than velocity. So velocity can be positive or negative because it depends on the direction it's going, but speed is always positive, so it's an absolute value. Acceleration of the object at time t is given by the derivative of velocity, which is the second derivative of position function. I think we've seen that before though. Okay, so in this first one, it says a ball is dropped from a height of 64 feet. Its height above the ground in feet t seconds later is given by S of t equals negative 16t squared plus 64. So here's a nice graph of it. And we're supposed to figure out the instantaneous velocity of the ball when it hits the ground, and what is the average velocity during its fall. So for our instantaneous velocity, so we have that S of t is the negative 16t squared plus 64, and I know I'm just copying down from over there. And our velocity is going to be the first derivative of the position function. Let me slide this over a little bit. And that's going to be negative 16 times 2t plus 0. So our velocity is going to be negative 32t. So the question is, when we're at 2 seconds here, this is time on the x-axis. So our velocity at 2 seconds, that's when the height is 0, when it hits the ground, is going to be negative 32 times 2, which is negative 64, and this is in feet per second. And then our average velocity is going to be the position at 2 seconds minus the position at 0 seconds over, and then we are at 2 seconds minus 0 seconds. So the position at 2 seconds is 0 because we're at the ground. Position at 0 seconds is 64 because that's where we begin, 64 feet above the ground, over 2 minus 0. And that's going to be negative 64 over 2, which is negative 32, and it's in feet per second. So that's pretty interesting that the instantaneous velocity is negative 64, but if you average it, it's 32. It's half. So pretty cool. Interpreting the relationship between velocity and acceleration. A particle moves along a coordinate axis in the positive direction to the right. Its position at time t is given by S of t equals t cubed minus 4t plus 2. Find the velocity at 1 second and acceleration at 1 second. So we have velocity at time t is the first derivative of position function, which is going to be 3t squared minus 4. And then our acceleration at time t is the first derivative of velocity, or the second derivative of position. There's 2 tick marks there. And that's going to be 6t. So our velocity at 1 second is going to be 3 times 1 minus 4, which is negative 1. And this is in, do they give us units? I don't see units. So negative 1 unit per unit of distance times over the unit of time. Acceleration at 1 second is going to be 6 times 1, which is 6. So the key here to answer is A and B. A says, is the particle moving from left to right or right to left at time t equals 1? Since the velocity at 1 second is negative, it's moving right to left. And B, is the particle speeding up or slowing down? Well, since the velocity or the acceleration is positive, it's 6, so it's accelerating in the opposite direction, which means it's slowing down. It's slowing down. Okay. Let's go on. Similar problem here. The position of a particle moving along coordinate axis is given by s of t equals t cubed minus 9t squared plus 24t plus 4, where t is greater than or equal to 0. So find our velocity. So again, v of t is going to be the first derivative of the s function. So 3t squared minus 18t, that's 2 times 9 is 18, and then plus 24. At what times is a particle at rest? So we look for 3t squared minus 18t plus 24 equals 0. And I notice that you can divide a 3 out of everything here. So I do. So it's t squared minus 6t plus 8 equals 0. So this factors to be t minus 4 times t minus 2 equals 0. And by the zero product property, we can set each of these equal to 0. So t minus 4 equals 0, or t equals 4. T minus 2 equals 0, or t equals 2. Okay, so that's when it is at rest. On what time intervals is the particle moving from left to right and right to left? So for that, I went ahead and I just thought about this graph. This is a parabola that is opening up. Therefore, I mean, you can make this more complicated, but it's as simple as we know it crosses at 2 and 4, and if it opens up, it's positive from 0 to 2 and from 4 to infinity. But from 2 to 4, it's negative. Excuse me. So it's going left to right, left to right, from 0 to 2, and from 4 to infinity, and then it's right to left from 2 to 4. Use the information obtained to sketch the path of the particle along the axis. So if you were to go along, and I mean, we're starting at time equals 0. Oh, no, there's my dead spot on the screen. So we have, we're doing position though, so this is 0 position. And if we pace this out by 4, it's 4, 8, 12, 16, 20, 24, 28. If we go back and think about this position function, and if we think about the position at 2, we are at 24, if I plug it in. Position at 4 seconds is going to be 20. So that means, and position, the initial position is at 4. So we start at 4. We start at 4. We're trucking along here. Then at 24, it takes that turn back to 20. Then it turns again, because this is our S of 2, and this is our S of 4, where the velocity goes negative for that bit, and then it goes positive again. Okay, next one. So particle moves along coordinate axis. Its position at time t is given by s of t equals t squared minus 5t plus 1. Is a particle moving from right to left or left to right at time t equals 3? Well, our velocity at time t is the first derivative of s. So I get 2t minus 5. So the velocity at 3 seconds is 2 times 3 minus 5, which is 6 minus 5, which is 1, which is positive. So that means it moves left to right. Okay. The equation for free fall at the surface of some planet is, S is in meters, T is in seconds, is 2.6 T squared. How long does it take a rock falling from rest to reach a velocity of 33.8 meters per second? So we have our position, our velocity is going to be the first derivative again. So that's going to be 2.6 times 2t or 5.2t. So we just take that 5.2t and set it equal to the 33.8 divided by 5.2. Time would equal 6.5 seconds. Okay, let's keep on going. Population change. Population growth rate is the rate of change of a population and consequently can be represented by the derivative of the size of the population. Fortunately for these problems, we're going with the constant population change. If P of t is the number of entities in the population, then the population growth rate of P of t is divided by P prime of t. So the population of a city is tripling every 5 years. If its current population is 10,000, what will be its approximate population 2 years from now? So it's always going up by 10,000. It's not going to go, not an exponential increase. So our initial population is the 10,000. Our population in 5 years is triple, so it's 30,000. So we want to get that rate of change. The rate of population change at time 0 is going to be population at 5 minus the population at 0 divided by 5 minus 0. So it's going to be 30,000 minus 10,000 divided by 5. So 20,000 divided by 5 is 4,000. So 4,000 people a year. So our population at 2 years is going to be approximately population at 0 years plus the 2 times the change of population. See what we did that earlier? So that's going to be 10,000 plus 2 times 4,000. So I get 18,000. That's it. Okay. Now for the next one. Same type of problem. The current population of a mosquito colony is known to be 3,000. So our P of 0, they tell us, is 3,000. And if P prime of 0 is 100, estimate the size of the population in 3 days. So the population in 3 days is approximately the initial population plus 3 times the rate of change of the population. So we're looking at 3,000 plus 3 times 100, because the rate of change was given to us as 100. And that's going to be 3,300. Okay. Let's talk about changes in cost and revenue. So some key takeaways here. Marginal cost is the derivative of our cost function. Marginal revenue is the derivative of the revenue function. And marginal profit is the derivative of the profit, which is the difference of the revenue derivative and the cost derivative. Here's an example for us. So it says, assume the number of barbecue dinners that can be sold, X, can be related to the price change P by the equation P of X equals 9 minus 0.03X, where X is between 0 and 300 dinners. In this case, the revenue in dollars obtained by selling X barbecue dinners given by R of X, revenue, is the number of dinners times the price. That's how much money comes in. So revenue is not profit. Revenue is the money coming in. So that's our X times our P of X. This is just P of X. And they distribute that through. They get negative 0.03X squared plus 9X. So use the marginal revenue function to estimate the revenue obtained from selling the 100 first. So we can figure out what the revenue is for the 100th and estimate what the next one's going to be. So let's see. Our marginal revenue, it means revenue on the per item basis, is going to be R prime of X. That's an R. And that's going to be negative 0.06X plus 9. So we look at the R prime of 100. What was it at 100? And that was negative 0.06 times 100 plus 9. And for that we get 3. So that means the revenue on the 100 first, or 101 minus 100, that isolates it to the 100 first one, is going to be, let me slide this over here, 602.97 minus 600, which is 2.97. So it's $2.97. And that's pretty close to that, the revenue calculation there. So our estimate was $3 and the actual calculation was $2.97. So I was comparing it here. Okay, our last example from this section. Suppose that profit obtained from the sale of X fish fry dinners, that was barbecue before, now it's fish fry, is given. Now they gave us the profits. So we have P of X equals negative 0.03X squared plus 8X minus 50. Use the marginal profit function to estimate the profit from the sale of the 100 first fish fry. So we're looking at P prime of X, or I should say the marginal is going to be P prime of X, and that's going to be negative 0.03 times 2x plus 8, or negative 0.06x plus 8. So if we're looking at P prime after we've done 100 of these, that's negative 0.06 times 100 plus 8 is going to be negative 6 plus 8, which is 2. So this approximates the P of 101 minus P of 100. So what that's saying is it's the 100th dinner and what's the profit going to the next one. So anyway, there we go. And hope you enjoyed this applications rates of change.